At the core of cost accounting is a simple axiom. Financial expenses are rarely static numbers. Instead, they are dynamic behaviors, governed entirely by the volume of production activity happening on the floor. Take raw materials and direct labor. These are variable costs. They scale in direct proportional lockstep with production volume. If output doubles, the total cost of these inputs doubles. The mathematical rule here is strict. While total variable costs increase as volume grows, the variable cost to produce one single unit remains perfectly constant, regardless of how many units roll off the line. Fixed costs behave in the exact opposite manner. Foundational expenses like facility rent, interest, and lease payments remain completely unchanged in total. Even if production halts entirely and output drops to zero, the company still owes the exact same amount. Because that total fixed dollar amount doesn't move, the fixed cost assigned to each individual unit actually decreases inversely as production volume increases. The more you build, the cheaper each unit gets to support. But these definitions only hold true within a strict boundary condition known as the relevant range. The relevant range defines the physical and operational limits within which these cost behaviors remain completely reliable and predictable. It is established by the specific efficiency of a company's current manufacturing plant capacity and its existing agreements with labor unions and suppliers. Pure fixed and pure variable costs are theoretical extremes. To build an accurate predictive model, analysts must account for the messy reality of the ledger. Most corporate expenses contain elements of both simultaneously. We call these mixed or semi-variable costs. They fuse a flat, unchangeable base fee with an additional, activity-driven variable rate. Consider a standard production line efficiency upgrade. A company decides to rent specialized machinery. This table breaks down the contract. The rental requires a flat $150,000 fee plus $1 per unit. At zero output, the cost anchors at $150,000. As output scales to 10,000 units, total cost rises linearly to $160,000. If we plot this data on a graph, the behavior becomes clear. The $150,000 base forms the y-intercept, starting the line well above zero, while the $1 per unit charge forms the constant upward slope. Because mixed costs conflate two distinct mathematical behaviors into a single line item, they create a forecasting blind spot. Before an organization can set accurate budgets, these two behaviors must be algebraically decoupled. In a real-world scenario, the distinct fixed and variable components are rarely handed to you in a neat contract. They are hidden within historical accounting records. This table shows a 6-month historical data set tracking factory maintenance costs mapped directly against machine hours from April through September. The data is inherently volatile. The costs clearly fluctuate with the machine hours, but they do not move proportionally. This proves we are looking at a semi-variable expense. The analyst's imperative is to look at this limited historical sample and isolate the exact base maintenance fee from the hourly variable wear and tear rate. There are two universally accepted accounting methods for estimating these mixed cost components. The first is regression, or the scatter graph method. It plots every data point to find a line of best fit, making it highly complex and highly accurate. The second is the high-low method. It trades a slight degree of accuracy for operational speed, allowing for rapid estimations. We will deploy the high-low method here. The high-low method operates on a specific principle. The clearest signal of cost behavior exists exclusively at the extreme absolute poles of historical operational activity. Step 1 of the high-low method requires mathematically isolating the pure variable portion of the mixed cost. The core rule of selection is strict. The analyst must identify the periods with the highest and lowest activity levels, the cost drivers on the x-axis, regardless of the total dollar amounts. Scanning the data, we locate the absolute peak of activity. That occurred in May, driving 1,600 machine hours at a cost of $3,400. Next, we locate the absolute floor of activity. That was July, driving 800 machine hours at a cost of $1,900. To find the variable rate, we must calculate the exact difference between these two operational poles. This equation shows the formula. The difference in cost between the high and low periods is divided by the difference in the cost drivers between those same periods. Walking through the numerator, subtracting July's $1,900 cost from May's $3,400 cost yields a total cost difference of $1,500. In the denominator, subtracting July's 800 hours from May's 1,600 hours yields an activity difference of exactly 800 hours. Dividing the $1,500 difference by those 800 hours results in $1.87. This $1.87.57 represents the pure variable rate per machine hour. Geometrically, it is the exact slope of the line connecting the highest and lowest nodes of production reality. With the variable rate secured, step 2 is to calculate the unchangeable fixed portion of the maintenance cost. The logic relies on the total cost equation. Total cost always equals fixed cost plus total variable cost. The algebraic maneuver is straightforward. If we subtract the total variable cost from the total cost at any known data point, the residual amount left over is the pure fixed cost. We can select the low period, July, to test the formula. Using the high period of May would yield the exact same mathematical result. First, we calculate the total variable cost for July by multiplying the 800 logged machine hours by our newly derived rate of $1.87.50 per hour. The total variable cost for that specific month was precisely $1,500. We then subtract that $1,500 variable cost from July's reported total cost of $1,900. The remainder is $400. By stripping away the known variable expenditure, the analyst successfully exposes the hidden, static $400 base fixed cost anchoring the dataset. These two isolated variables are immediately useful. Management uses them to forecast future budgets with precision. Consider a hypothetical scenario. The operations manager plans to run exactly 1,300 machine hours next month and requires a precise budget projection. We simply plug the projection into our derived model. We take the $400 fixed base and add the 1,300 hours multiplied by 1.875. The probable total cost for next month will be exactly $2,837.50. This table shows cleaning expense data, demonstrating that this logical framework is completely agnostic. The analyst simply repeats the algorithm, isolate the high hours in January, identify the low hours in March, and extract the slope. The high-low method is a universally scalable algebraic framework for converting historical accounting noise into predictive operational intelligence. There is a critical professional warning attached to this technique. This beautifully linear predictive model is entirely fragile. Remember the constraint established at the very beginning. Cost behaviors are strictly bounded by the relevant range. Consider the breaking point. What happens if demand skyrockets and the company is forced to lease an entirely second assembly line to double its capacity? The baseline fixed cost will not remain constant. It will jump violently upward as the new lease is signed, creating what is known as a step cost function. A step cost function is a nonlinear reality. Costs remain constant over small ranges of output, but they increase by discrete, sudden amounts as massive new capacity comes online. Mathematical projections are only as reliable as the physical boundaries of the manufacturing plant. The moment a company outgrows its relevant range, the geometry of cost behavior fractures, and the analyst must build the model all over again.